Hi everyone, this is Samer Al-Haj Mahmoud from Arm presenting today the Arm SystemReady SR and ES standards for servers and the edge. So Arm SystemReady is a compliance certification program established by Arm that brings a level of consistency for the Arm ecosystem across devices. Started initially with focus on the servers, infrastructure edge, and IoT edge sectors. The vision of Arm SystemReady is that software just works seamlessly across the devices in the ecosystem, focusing on solving problems in the common components, the hardware, the middleware, the firmware, and the OS, and the hypervisors in order to establish a uniform consistent way of booting the system and deploying standard operating systems, allowing partners and the ecosystem to focus on innovating and deploying the workloads and differentiating levels of application software. And as you can see in this graphics, the vision of software just works extends across from the high-performance IoT devices to the cloud edge, instead of the picture on the left, where traditionally these devices have their own hardware and firmware boot loader and custom OS stack through maybe a vendor-specific SDK. You move to a more uniform, compliant hardware implementations and firmware implementations, allowing running the common OSs and the common workloads across different devices from different vendors. Arm SystemReady is a key component of the Arm project Cassini and part of the enablement to the ecosystem for that project. So let's take a look at what are the key ingredients of the Arm SystemReady, starting with the key specifications. The first and very important specification is the BSA, the base system architecture. This is the hardware baseline, the requirements for a minimal set of CPU and system architecture features that are necessary to provide a common expected hardware components for the OS to boot and run. So that may include things such as integration of the PCIe standard in the SoC. It's generic. It works across the segments with the goal of having segment-specific supplements, such as the SBSA for servers. The supplements could add additional requirements and features in the hardware that are specific for that segment. So in addition to the BSA and the SBSA, we have the firmware requirements, and the main specification, the top level specification, is called the BBR, the base boot requirements. The BBR is a set of firmware rules that include multiple recipes, and we'll talk about these next. It defines standard interfaces leveraging ARM specifications such as PSCI and SMCCC, as well as industry standards like UEFI, ACPI, SMBIOS, and then builds recipes that are tailored for different classes of operating systems across the ecosystem. So you have, for instance, the SBBR recipe, which is, if you're familiar with the existing server-ready program before SystemReady was introduced, and the SBSA and SBBR specifications, the SBBR recipe in the BBR spec is essentially the same as the previous SBBR specification. It leverages the standard UEFI, ACPI, SMBIOS, as well as the ARM interfaces, PSCI and SMC, and just continues that same level of firmware standard expectations from servers to embedded servers and edge and even IoT devices. In addition to SBBR, we have the EBBR, which is a recipe that refers to the EBBR specification. The EBBR spec is an open source community developed spec that Arm and Linaro and the community participate in building, which focuses on tailoring some of the UEFI requirements for embedded devices. So you have the SBBR recipe and the EBBR recipe. In addition, we have placeholder and the recipe for Linux boot firmware requirements for servers that require booting with Linux boot as the firmware implementation. So BBR specifications, recipes. We also have related specifications around security. So the base boot security requirements, which adds additional UEFI and firmware requirements around UEFI secure boot, secure capsule update, and TPM usage and exposing TPM to the operating system. So with these different specifications and recipes, we build the different bands of the SystemReady. They are all part of one program, the SystemReady program. So you have SystemReady SR, LS, ES, and IR. So what does all of this mean? SR is servers. It's equivalent to the previous ServerReady program, uses SBSA and SBBR as the main requirements. SystemReady LS is for Linux boot servers. So while the hardware needs to be SBSA server requirements apply to the same servers, whether you are targeting SR or LS, the firmware could be Linux boot based with LBBR. The two other bands target the IoT and embedded and edge class of devices. You have SystemReady ES, which just is based on the BSA specification, so no need for the additional server requirements that come with the SBSA, but it uses the same SBBR firmware requirements as the ServerReady or SR. So both SR and ES use the same firmware requirements. And then finally, we also have SystemReady IR, which is also built upon the same BSA foundational requirements, but uses the EBBR firmware requirements rather than SBBR. So focus of this presentation is we are going to talk about SystemReady SR and ES. The session right after this is actually going to also talk dive deeply into SystemReady IR. So with SBBR, you leverage these three main standard interfaces to NOS, UEFI, ACPI, and SMBIOS, using either open source firmware implementations like TianoCore EDK2 or commercial firmware provided by BIOS vendors, for instance. And you establish this SBBR contract that allows you to boot standard off-the-shelf operating systems ranging from all the various Linux distros, VMware, Windows. Remember, the goal is it just works. So ideally, with the standard SBBR and BSA and SBSA compliance, these can be existing distros, last year's distros, off-the-shelf standard operating systems. No need for special custom engineering in the kernel or in the for a future OS distro to be able to boot on this device if the compliance rules are met. So if we look closer between ES and SR, you'd say, well, they are both based on SBBR. They are both targeting booting essentially the same operating systems. So what is really the difference? Why can't we just have SBSA and SBBR and just make it one band? Why do we need two different bands for ES and for SR? And it really boils down to the hardware compliance level. So if the silicon was built with SBSA in mind, with SBSA levels through 3 through 6, Then with an SBBR firmware, you are already talking about a server-like or server-compliant platform, even if the platform itself is not a server. So it's called SR or server-ready, but it can be implemented in any footprint as long as the silicon is compliant to the standard. Where ES gives some flexibility is, first of all, the hardware compliance, the requirements are lower than the SR because it is just based on the BSA, the base system architecture specification, without the additional SBSA rules on top of BSA. So that's the first key difference. And then the second is the waivers for existing hardware. So if existing silicon that was not built with BSA rules or SBSA rules in mind and has compliance issues, depending on the firmware implementations, the workarounds in the firmware, on how much it can achieve the vision of system-ready booting, the standard of the shelf OSs on the device. With ES, you could consider some of the waivers for existing hardware versus the more strict requirements with SBSA and SR. Certification requirements are very similar. They both run the same architecture compliance test suite, and we'll talk about that in the next slide. So for now, if you are trying to certify an SR or an ES system, you can use the same certification test suite to collect the results. Like I said, in terms of hardware requirements, SRs adds SBSA levels 3 to 5 in addition to BSA, while ES stops at BSA, but it could also include SBSA level 3 without the server requirements. Since it's using the same test suite, if you run the test suite at SBSA level 3, then the test suite is going to list all the server level requirements from level 3, and those, not all of them may apply for an ES, so some manual examination of the test results is needed because the test suite is not tailored completely for just BSA as of today. In terms of firmware, it's really exactly the same with just both SBBR, with just the difference of some level of waivers or exceptions may be allowed for ES, depending on the existing silicon and where it stands in terms of hardware compliance. OSs that are booted, the SR requires booting Windows, at least with WinPE, and recommends VMware and requires 2 Linux or BSD distributions. ES recommends booting Windows and VMware, so at least it has to be attempted, and if there are failures, it need to be looked at, but they are not a hard requirement for certification. And then the same level of Linux distros apply to ES as it does to SR. We talked about the certification compliance test suite. This is an open source test package available from Arm. You can build it from source. You can download the pre-built binaries. The pre-built binary, you can flash it to a USB key or to USB SSD, for instance, or even to an SD card or an eMMC partition, and just start booting from it. It reboots many times, runs in portions in the UEFI shell and portions boot to Linux that's included as part of the test suite, tests the SBSA compliance, the UEFI API compliance using the self-certification test, and the ACPI and SMBIOS and some of the runtime OS calls compliance using the FWTS or the firmware test suite. The goal is to move the ACS compliance suite into a modular test suite that works for the various bands of system-ready, because of there are a lot of commonality in terms of requirements, but also some subsets of requirements, if I may say, across the bands. So the goal in the second half or around mid of this year is to start releasing the ACS compliance suite that is tailored to different bands in SystemReady. On the ARM webpage for SystemReady, you will see what we call the SystemReady certification list. This is a listing where certified systems show up. It includes the manufacturer, the product that was tested, the firmware level that was used for testing, what SBSA or BBR level was tested, and even the operating systems that were included in the test. So let's take a quick look at some of the devices that are certified today, showcase them, and maybe highlight some key firmware development activities around those devices. So the first is the Ampere Ultra Mount Jade server. This 2-socket server based on the Ampere Ultra processor. This is the first server that was certified as SystemReady SR, the only server certified or the first server certified with SBSA level 4, booted with multiple operating systems, as you can see in this slide. The Ampere Ultra firmware that is offered by Ampere to their customers include both commercial firmware stacks for the host firmware and the BMC firmware that are provided by AMI, as well as open source firmware, including TianoCore EDK2, Linux boot, as well as Open BMC firmware for the BMC. These are links to all the repositories and the upstreaming patches that are in progress. Some of these are forks on the Ampere GitHub that are a work in progress in terms of upstreaming, for example, to TianoCore or to the OpenBMC projects. Next is the Gigabyte Ultra Mount Snow. So this is a 1-socket server from Gigabyte that is also built using the Ampere Ultra SoC. The server was certified recently with SBSA level 4 and boots multiple operating systems, including, as you can see, Windows and various Linux distributions. So those were some examples of SR certified systems. If we look at on the ES band, we'll find a range from really small IoT devices to maybe higher end edge gateways. The first example is the Raspberry Pi. The Raspberry Pi 4, the default firmware that comes with the Raspberry Pi is not SystemReady compliant. However, a group of the open source community, the Pi Firmware Task Force or PFTF, worked together on building a TianoCore EDK2 firmware that is compliant to UEFI, ACPI, and SMBIOS, SBBR, fully open source and upstream. It is SystemReady ES certified. It's the first system that was certified for ES, and it can boot a wide range of operating systems, including VMware ESXi on ARM, Windows IoT Enterprise, and various Linux distros. You can read more about the Raspberry Pi firmware community effort and project on the blog rpi4-uefi.dev. There is a Discord, a developer ecosystem Discord server that has a channel dedicated for the rpi4 UEFI project. You can see that TianoCore upstream, the firmware is actually built directly from the code that is upstream to TianoCore. We even have issue tracker that's open source, and the test results are even uploaded to GitHub. And some screenshots to just showcase the various OSs running on the rpi4, said from everything from Linux, VMware, and Windows. NXP Layerscape 2160 is another key device that is certified with the Arm SystemReady ES. NXP, the RDB is a reference design board. It is tested with VMware and different Linux distros, and it's available. Firmware is available directly from NXP, as well as from open source projects. So Parts of the firmware, the UEFI firmware, for instance, the SBBR compliant firmware, are available on NXP code repositories. Some of it are upstream to TianoCore, or upstream is a work in progress. The SolidRun Honeycomb, based on the NXP 2160 SoC, is another system that is undergoing SystemReady ES certification. There is a very active Discord community channel on the Discord developers community server. The firmware is all open source, available at the links in this presentation, and is tested with a large range of OSs, including VMware, Windows, and all the different Linux distributions. Again, still under active development by SolidRun and the community, and upstreaming planned, and the certification is in progress. Two other devices that fall in this category are the NXP 1046, on the slide says 2160, but it's the Layerscape LS 1046, both the RDB and FRWY. These are smaller footprint IoT networking gateway devices that, and again, open source available from NXP. Some of it already upstream to TianoCore EDK2, and certification is in process. SBSA QEMU is being done by Linaro and the community to have the SBSA ref machine for QEMU, supporting SBSA hardware requirements. It is code is already upstreamed, and the work in progress for additional firmware changes and the hardware model changes are all happening upstream. There are even test results for running the ARM architecture compliance suite and the UEFI test suite on the device. Take a look at it. It's a very interesting work that is aiming at being SBSA and SBBR compliant. Finally, I mentioned some effort that is done by SemiHalf and SolidRun to fully support UEFI and ACPI and TianoCore on the Marvel Octeon TX2 board using the SolidRun SolidRun-based board. This was presented in the past by Marcin Wojtas from SemiHalf. The code is already upstreamed, and more patches, more work is going on this project. That's all. Thank you so much for listening. If there are any questions, maybe we have a minute. If there are any questions in the chat, I could help answer them. Are there any requirements for certified vendors to publish what works? For example, what boot media firmware supports, etc., etc. We encourage the vendors to publish user documentation and recipe. In the system certification list, when we certify a platform, we call out the specific firmware revision that was used for certification and a link to that firmware from the vendor, or from the device manufacturer, or from the open source firmware if the firmware is supplied by the open source community. There might be errata or some waivers published by ARM as well that detail if there were certain workarounds or restrictions to run the certification. For instance, that could be limiting what media was used for this certification. But in general, it's something that the vendors should be providing as documentations to the users. All right. Thanks, everyone.